Hi and welcome to the video lecture series on contact mechanics in the course M7033T, Scientific Computing with Applications in Tribology. So this is the fourth continuous and discrete convolution part of the fourth video lecture on the application Fourier's technique and Fourier techniques and multi-level multi-integration in contact mechanics. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. In this part, we will start with the integral equations in general, then see how the continuous convolution is a special case of this, and the reason why we're going to talk about continuous convolutions in the first place is that it allows for application of Fourier techniques for the solution of it. We will then have a look at how an integral equation can be transformed into a convolution, and then how subsequent DFT can be applied to solve the problem, the so-called CC-DFT method. Then we move on to the discrete convolution, and here we start with the linear one and then move on to the circular, which will be of much more interest in contact mechanics as we can represent the elastic deflection by means of a circular convolution, and a circular convolution allows for subsequent fast Fourier transformation techniques to accelerate the computation of it. As in any calculus course, you learn some fundamental elementary operations, then you learn how to differentiate things, and then you learn how to integrate things. And now we're on this integration level, and we will devote this to convolutions. So we have continuous convolutions, and a continuous convolution is actually a subset of or an integral equation that may be looking like this. So we have an integral of two functions, one which we will refer to as a kernel is a function of x and the dummy variable s, and then we have a function f which when we integrate over the dummy variable s, and when we do, we obtain the function gx. And this is a continuous equation, continuous integral equation. And what we now will look into is possibilities of finding a transfer function which, if we take this transfer function being the Fourier transformation of the kernel and the Fourier transformation of the function, put them together just by multiplication in the frequency space, then we obtain the Fourier transform of the function g of x. This would be nice if we could find that h of omega function, because then if we use the IFFT, we could get back to gx. So without knowing gx in advance, but only the kernel and the function, and if we knew, and also, well, we also need the transfer function h omega. So if we knew that, then we could just perform plain multiplication h omega f omega and then take IFFT to get g of x. You will later on see why this will be interesting, because if we can do this with the FFT, we will actually reduce the complexity of performing this computation. Here it will be a little bit more concrete. So if we take G and its discrete representation, GIN, so we have discretized G on n nodes, then we can represent this in summation form by just summing the values of the kernel Kij with Fj's from j equals 0 to n minus 1 to obtain our result Gi. Now, if we knew that transfer function h of omega, we can discretize it, and we can denote the discretized version of it as hk, where k is then the discrete frequency, the wave number. And now we have the discretized transfer function, and if we just FFT our discrete signal f, then we get a discrete Fourier transform in terms of the wave numbers, and we can put them together, plain multiplication, as we did with the Fourier differentiation, and then we obtain Gk, which is the Fourier transform of Gi, the original function, and we use FFT to obtain Gi again. So this could be useful because this first summation operation is actually n squared operations. But this one is just n, or FFT is n log n and IFFT is n log n, but that's just 2 n log n number of operations. Plus, well, the n operations to multiply hk with fk. So all in all, the FFT then multiplication with the transfer function and the IFFT is of the order n log n. So think of n being a number 1000. The discrete summation would take you 1,000,000 operations. If you did it with the FFT approach, you would be down at 3000, or well, 2 times 3000 plus very few, 3. So around 2 times, around 6,000 operations instead of 1,000,000. Okay, the continuous convolution, it is a special case of the integral equation that we considered just before, when the kernel is just is not a 2-variable function, but it's only a function of 1 variable really, but shifted, but considered shifted when we are placing it into the integral equation. So h of x minus s times fs now renders gx. And this is recognized as a continuous convolution. And what is nice with this is that it guarantees that you can take the Fourier transform of this kernel h. So lower letter h becomes capital letter H of omega when you Fourier transform it, and then you just multiply this with your Fourier transformation of f, you IFFT this, and you get g of x. So this is nice. And here is just the definitions then of h of omega and f of omega. Okay, a small detour perhaps, but it's quite interesting to look into the result of Westergaard, which are very old results. He really knew what to do with pen and paper, and he considered a sinusoidal pressure he considered a sinusoidal pressure to be loaded on the half space, and by denoting this by A sinus omega x, he found that it gave rise to displacements or deflection or deformations on the form that we see here. So plugging in P of S equal A sine omega S into this integral equation, which is quite similar to a continuous convolution, which we will see later on, then he obtained a closed form result. And we can note, of course, that okay, we have this factor in front here, and what we see really here, the result is just this auxiliary type of representation of the deflection as we have been defining before, and then we have the additional constant here. So because of this, we now know that it must be so that the transfer function h of omega, it must just be 2 over E star omega. We can read this directly from the closed form result of the deformation. And we can of course obtain now by straightforward multiplication between the transfer function h omega and the Fourier transformation of the pressure, we can obtain the Fourier transformation of the deformation. Okay, putting things together means that we, in the frequency space, have the deformation u, or the auxiliary representation of it at least, equal to the transfer function h, which we exactly know what it is, and p, the Fourier transforms of those. And that means that we can obtain p by just dividing u with the transfer function. Knowing this, and that h is exactly represented by 2 over E star times omega, we understand that p must be proportional to the frequency. And we can also see, by what we learned before, that I omega u is just the derivative of u and the Fourier transformation of that. So it means that the pressure is related to the derivative of the deformation. Now this way of obtaining the deformation is numerically exact for a pressure which can be represented by a Fourier series. But in the same way as the derivative is not preferred with unfiltered data, if it not goes through a Fourier series filter before, it's not preferred. Discrete convolutions, what are they? If we have a continuous convolution, we can of course discretize it, and in summation form it looks like this. And if both signals h and f are of length n, the values of h outside the interval 0 to n minus 1 must be considered as 0. So more precisely, we get G as the signal of length 2n minus 1, and it's then given by precisely what we saw before. So it's given by the sum from j equals 0 to n minus 1 of hi minus j times j, and then for all the i's from 0 to 2n minus 2. As usual, it's easier if we have a concrete example. So if we now let h and f be two vectors of length 3, then we denote now the convolution of them as gi3 for this purpose, and the summation will then be from 0 to 2, 3 minus 1, and what we sum is, well, it's h of I minus j times fj for I equal 0 and to 6 minus 2, i.e. 4, so it will be a signal of length 5, which is 2n minus 1. And now here we have the first setup. And now you see what I meant with considering the values of h outside the interval as 0. Because if we take I equals 0, then we have when j is 0, we have j equal I equals 0, and then we should perform the multiplication by h naught and f naught. Okay, but then we increase the summation index j to 1, and then we have 0 minus 1 because I is 0, and that's minus 1, and we don't have a value for h at minus 1, we put it 0, and therefore when we multiply, this factor will not count, it will be 0 of course, and the same goes for the next one, which is outside the interval, meaning that our first element in G would be f naught h naught. Then if we increase I, we have for the first summation index node, we have 0, we have 1 minus 0, and that's 1, so we multiply f naught with h1. Now second summation index 1, then we have 1 minus 1 is 0, and we multiply f1 with h naught, and that is also contributing to the value of g, this point. And finally we consider j equal to 2, sorry, and then we have, of course, 1 minus 2 is minus 1, and we sum we multiply f2 with 0, and it doesn't contribute to g, so g1 is just f naught h1 plus f1 h naught. Okay, third index I equal to 2. All the differences between the I and j indices lies within the interval, and G2 is consequently the sum of the product between f naught h naught plus f1 h1 and f2 h naught. We increase the index I to 3, and then we get the first point outside the interval, and G is just the sum of the two other ones, like this. And the fourth and last, or the fifth and last summation index, I equal 4, then we only have one point within the interval, and which is counting to G4. This means that we can formulate the summation above here as a matrix vector multiplication with the matrix given here. So it's a 5 by 3 matrix, which when we multiply by the 3 times 1 vector, column vector f, will give us the column vector, the 5 by 1 column vector for G, which we just have seen in MATLAB. Okay, so MATLAB has a built-in function, conv. Okay, so we take two signals, h is 1, 2, 3, and f is 1, minus 1, and 2. And we convolve those by means of MATLAB built-in function conv. Then G, which is then the output, would be a 5-valued vector. And here, as I have represented these two h and f as row vectors, G will also be a row vector, and it will be exactly this row vector. Alternatively, I could have defined the 5 by 3 matrix just by circulating that h row, that row of values of h, and I can then multiply with f prime. I take the transpose, and here I don't bother about the conjugate, so just the transpose, and then transpose it again to get it to a row vector, which is of course then identical to what we got from the built-in function conv. In the linear convolution, okay, the values of h and f outside the interval are considered as 0. We could switch the summation index, the dummy index j, between h and f, and therefore either h or f outside the interval should be considered as 0. Now, think of applying this to a periodic function. It would be detrimental, as it would violate the periodicity. And this means that we cannot apply an FFT to the linear convolution. Or we can of course, but we would get a very strange result, not the expected one. So instead, to have a good result for a periodic function, we have to apply a circular convolution. And if we have two vectors, h and f, now the good thing with the circular convolution is that the inverse DFT of the product of the vectors DFTs, as we have seen before now many times, renders exactly the same result. So we can actually accelerate the computation of a circular convolution by means of FFT. Okay, now from now on we will use the following description for the circular convolution between two periodic vectors of length n. So now we have two vectors, they have the same length, and the length is n. Okay, and now the definition reads that the circular convolution G between those vectors is given by the sum of h, and instead of just I minus j, we now put there I minus j modulo n. So and we will demonstrate exactly what this means later on, but I'm sure you are very well familiar with the modulus function at this point. And now this is interesting in some sense. It has one more interesting aspect, because G will be a signal of length n in this case. So not 2n minus 1 like in the linear convolution case. Let us look back at the periodic window. So periodic signal is defined by the values within this periodic window, here marked in red. So we have an n long signal h from h0 to hn minus 1. Now outside of this periodic window to the left, we have a repetition of the last part, of course, of this periodic window, and to the right we have a repetition from the first part of the periodic window. This means that in matrix form we have h to the modulo to the n modulo of I minus 1 expressed like this. So on the first column we have h nod and all the way down to hn minus 1. To obtain the second column, we just circulate the first one step down, so the h node ends up on the diagonal and then follows all the points down to hn minus 2, and we move the last one from the first column, h minus 1, to be the first element in column 2, and so on. We repeat that all the way, all the n columns, and the last column would actually appear like this, with h node on its diagonal, which is also the element at the bottom right corner of the matrix. Again, an example. So let's consider the circular convolution example here, G3, which is now the summation of j from 0 to 2 of our H circular kernel of convolution, and then f. From I equal, or not from, for I equal 0 to 2. So we have f node, f1, f2, and for I equals 0, we know that j, the first summation index, when that is 0 and I is 0, then we also have modulo 3, 0, which is 0, and therefore we should multiply f node with h node. We increase the summation index j to 1, and then we get I minus j is minus 1, but modulo 3 of minus 1 is 2. Can you see this? I'm sure you do. So now we multiply f1 with h2. Again, we take next, we increase the summation index, and now it is 2 and 1 and I is 0. It means that I minus j is minus 2, and we have modulus minus 2, which is then 1. Okay, so what we are doing now with the modulus is that we're circulating the values of h. Okay, then the last bit of this summation would be to multiply, add the multiplication of f2 and h1 to it. So g node is equal to f node h node plus f1 h2 plus f2 h1. Okay, now we move up one step in our index I, so evaluate g1, and we just circulate h as the arrows indicated there, and therefore we get h1, h0, h2 on the positions. Okay, they was just shifted one step forward, and then h1 came from the last index to become the first one, and therefore the multiplication reads f node h1 plus f1 h node plus f2 h2. Continue. Now these are all three inside the interval, or inside the periodic window, we should say. So we just do the normal computation there, and this renders the final result, which is expressed here in summation form to the left, well, for each of g node, g1 and g2, and in matrix form on the right, where we clearly can see that we have this circulated kernel matrix H, with H naught on the diagonals, and then just circulating column 1. One step for each column. MATLAB example. Same signals as before. We have 1, 2, 3 as H. We have F equal 1 minus 1 and 2. Do the CC-CONV. I'm not entirely certain that all of you can do this. I believe this is in the image processing or whatever toolbox it's called. So you may not be able to access it. But if you do, the result would be 273. But we can directly formulate this matrix, this circular matrix, instead by just generating this column, which is then circulated. Trouble is, when you do generate it in one row like this, you have to start with the rows. I think. I don't know if there is any better way of formulating it directly, but my way of doing it is to consider, okay, the first row, second row, third row, but I of course take the first element here, 1, and then the first element behind the semicolon, which defines that I am in the second row, which is now, and then I do the element 2, and then on the third one, on the third row behind the second semicolon, I have number 3. So that's the column 1, 2, 3. Okay, and then you circulate that column, and that will be move the 3 up to first position, push 1 down, and then I have push the 2 down. So I have 3, 1, 2, and then the last one 2, 3, 1. Now again, multiplying this with F wouldn't work so well because F is a row vector, so I have to transpose it, and in order to get a row vector result I have to transpose the result, so therefore the 2 primes.